In this talk, we will look at cost optimization of commuter and regional aircraft. This talk is essentially the gist of my own PhD research, which I carried out at Cranfield University in UK way back in 1994 to 1997. So, the content of this talk is towards research orientation, and it looks at a combination of aircraft design and air transportation. It does not cover any contemporary topic or it does not cover any current issue, but it is a more research theme oriented talk. So, the outline of this presentation is as follows. We will first look at what is meant by commuter aircraft and regional aircraft, because the whole talk is about cost optimization of these kind of aircraft only. We will then move to a very generic concept in transportation called as the generalized cost of travel. We will look at the components of generalized cost for air travel in particular, because that is what we are currently concerned about. We will proceed with description of a computer program that I wrote called as CRAGER, what it does and what is its relevance, what are its various components. I will also show you a flowchart containing the various blocks of this particular code. We will then look at estimation of the cost of setting up and operating a small regional airport that is required to meet the demand of air transportation in a remote location. So, let us start with the concept of commuter and regional aircraft. Commuter aircraft and regional aircraft are aircraft which are used for short haul travel in air transportation. Now, short haul travel stands for a distance of up to about 500 nautical miles or nearly 1000 kilometers, a bit less than that, and aircraft with capacity of usually 100 passengers or less. Any aircraft that has much larger capacity or travels a larger distance with smaller capacity would not qualify as a commuter or regional aircraft in general. Now, if you look at most of the aircraft which are operated and are available in this category, you will find that they are generally of a twin engine configuration. The engine could be a turboprop or a turbofan depending on the market segment that you are addressing, but these will be two engines which are mounted on the wing or below the wing, such as this aircraft, which is a Dornier 228 new generation aircraft. You can see this aircraft has two turboprop engines mounted on the wings. Or you could also consider an aircraft like ATR 72-600, which also is a similar configuration. It has two engines, both of which are mounted below the wing, and the engines here also are turboprop. Now, these aircraft generally suffer from one major drawback, and that is they have very high costs per seat per unit distance. We normally call them as seat mile costs. This is because the total operating cost is shared by less number of passengers. So, you have the number of passengers in the denominator, and therefore, the cost per seat per mile reduces. Now, one may argue that since these are small aircraft and that too they are turboprop aircraft, their operating costs are also quite low. So even the numerator is quite low per trip. But interestingly, in air transportation, the operating cost does not increase linearly with the number of seats. In fact, it comes down when the number of seats increases. Okay. So the cost, what I meant is the cost per mile, okay, it comes down. The numerical value of the cost will be more for larger aircraft or aircraft which are not commuter or regional, such as the airliners or other transport aircraft, but the cost does not increase in the same proportion as number of passengers, which means if you double the capacity of an aircraft from say 100 to 200, it does not mean that the operating costs are going to be doubled. Okay. They will increase by maybe about 1.25, 1.3 times, not double. So the moment you make an aircraft smaller, the per seat per mile costs are going to definitely increase. So this is the major problem with these aircraft, but they have a very specific purpose. They are excellent for testing new and untried markets, because if you deploy a large aircraft such as say an Airbus A320 with about 179, 180 seats on these routes, then it's unlikely that you will get so many passengers on those routes. So you will fly mostly empty. You may get 15, 18, 20 passengers and you have 320, 180 seats in the aircraft. You are going to have a very, very poor load factor, and therefore you are destined to lose a lot of your bottom line in these routes. But these are small aircraft. Dornier 228, for example, has just 15 seats in one configuration and 18 seats or 19 seats in the other configuration. So, if you even fill 15 passengers, 18 passengers, you are going almost full. So that's why these aircraft, despite high seat mile costs, they have a very good advantage of being able to deploy on new untried markets to see how they perform. And then when the market demand increases beyond a threshold which will support a larger aircraft, one can withdraw these aircraft and deploy them elsewhere. By itself also they have operating costs are low, but the costs per seat per mile are very high. Now when you operate an aircraft on a short haul market, that is short distances, you encounter a very interesting phenomena, that it is not just important what configuration you fly, but it is also important how you fly, what flight profile you take. For a classical long range airliner, the flight profile is very standard. You will take off and climb to a comfortable cruising altitude of approximately 35,000 feet, 10-11 kilometers. Then you will continue to fly level for a very long distance till the amount of fuel that you have consumed makes it more economical for you to raise your altitude. Then you again fly like that for a long time till again you reach a stage when you have much lower fuel, so a higher altitude is better, and then you ultimately come down and land. In the case of a commuter aircraft or a regional aircraft flying short ranges, turns out that the optimum profile is a sawtooth profile, which means you take off from an airport and keep on climbing to an altitude from where if you start descending, you will hit your destination. So there is very little or no cruise segment in such aircraft if you look only at the fuel consumption as your target. Also, you have to keep in mind that the rate at which you climb, the rate at which you descend, all those parameters also strongly affect the fuel consumption. Another problem that you face with these aircraft is that they face very strong competition by other modes of transport like the rail or a bus or the automobile, either a hired car or even a personal car. Because when you are traveling short distances, it might be more sensible for you to use your own vehicle, because the time taken for you to travel is not that much large. Plus the convenience of your own automobile, you can start from your origin, you can straight away proceed to the destination and you can reach the destination and park your vehicle. That comfort you don't have in case of a commuter aircraft, because you need to first travel from your origin point to an airport, then you have to undergo security, check in your baggage if you have baggage, then you board the aircraft, wait till it takes off, depending on the air traffic congestion. After that it reaches the destination, again reverse, you have to come to the terminal, collect your baggage, take a taxi, go to the destination. When your journey distance is not very large, this hassle may be much more than what you would like to do. For example, let us take a classic example in India of a travel from, say, New Delhi to Chandigarh or Mumbai to Pune. Now, New Delhi, Chandigarh you can cover by road in about 3.5 to 4 hours. Okay, we have a wonderful highway available. You could even take a break and have a nice meal at Murthal on the way from Delhi to Chandigarh. When you go by air from Delhi to Chandigarh, imagine from Delhi, from your origin you have to go to the airport, how much congestion you will face on the road, then wait, then board the flight, reach Chandigarh. The airport is in Mohali, from there you travel to Chandigarh, another about 15-20 kilometers. Okay. You might say, forget it, I will just rent a car and drive, go directly by road, or I will drive my own vehicle. But this luxury you don't have when you want to fly from Mumbai to London or Mumbai to Paris. You cannot say I will drive, because other modes of transportation, even rail, you will not. Mumbai to Pune, there are so many trains. Delhi to Chandigarh, there are so many trains, and there are Shatabdis available, there are the new high speed Vande Bharat trains available. You will not like to really go by air. So you will travel to air from Chandigarh to Delhi only if you have a connecting flight, or if somebody is paying for it, so you would want to take advantage of that, or if you happen to live near the airport at both the places, origin and the destination, if they are near the airport, then yes, you might say it's not a big deal for me. But in general, a passenger will incur much more inconvenience, spend much more time in going by air on short haul distances compared to rail or bus or your own rented or personal automobile. So this is a problem. They have high seat mile costs, they have very stiff competition. Now, here is an image or images of some very popular aircraft. On the left hand side you have two commuter aircraft, the Beechcraft 1900D and the Jetstream J31. They are now both almost obsolete. We don't see them flying too much nowadays, but in their heydays they were very popular as commuter aircraft. On the right hand side we have some regional aircraft like the Bombardier Q400, which is still very popular and it is flying, and then you have Saab 340B, well, a little bit obsolete now, but still operating on some routes. The regionals are having around 36 seats in case of Saab 340 and about 80 seats in Bombardier. Now let us move to the concept of the generalized cost of travel. I have already touched upon it indirectly in my initial discussion when I told you that it may not be really worthwhile for a passenger to go by air on short haul distances. Why? Because when we are looking at options for travel, we always look at the total travel cost and not just one component, which is the fare that you pay. So there is a direct component which is the fare paid for various segments. For example, when I go from my residence in Mumbai to a location in Pune, then I need to take a cab to the airport, then I have to take a flight to the destination, and then another cab from the airport to the destination. So there are three direct fares which I am going to pay. Then there are some indirect costs which I incur. Time is money, and therefore whatever time I spend in travel is actually an opportunity cost which is lost. So if I really have a lot of importance for my time, there will be a lot of time cost incurred. Then there are costs connected with the infrastructure. For you to be able to travel by air, there have to be airports. For you to travel by train, there have to be railway lines, railway stations, the railway car itself. Similarly, for the road transportation, you need to have roads. Now, all of this costs money, and that money is the infrastructure related cost. When you set up a new route between two cities, you have to provide the infrastructure, and that has its own cost. Then there is a cost because of discomfort. Some modes of transportation give you a comfortable journey, so you can utilize it for maybe listening to music or catching up on some reading, etc. Or you can even just relax, you can just sleep and use it for relaxation. But there are some modes of transport where you might not be able to relax. A bus journey, for example, may not be as comfortable as a good train journey. In the train also there are many classes. Okay. So when you travel by the so-called general class, it's not comfortable. It's cheap, but it's not comfortable. When you travel by air-conditioned chair car or second AC, you can just sleep and recover on your sleep. So there is a cost related to how much comfort or discomfort you are subjected to when you are traveling. Now let us look at the indirect cost little bit in more detail. So there is a time cost, as I mentioned, the total time spent in travel. Now the time cost varies from person to person depending on how much value you assign to your time. If you are a student and you really don't worry too much about the value of time, you might say, I don't care if I go in 4 hours or 8 hours as long as I am paying lower fare. But if you are a very busy business executive or a very senior person, each hour of your time has got some value because you can utilize that for some other more productive activity. So you will have a higher value of time. But this is a function of many things. It's a function of your income levels. It's a function of what travel type are you incurring. Are you doing it on business or are you doing it on leisure? Is it official travel or is it personal travel? Then also time of travel. Are you traveling in the middle of the night when you want to sleep, or are you traveling when things are that way comfortable? So sometimes we say that, okay, I am taking a red-eye flight, which means a flight that operates during night hours, makes you lose your sleep. So you arrived red-eyed at the destination. But I take it because I value my money more than my comfort. Okay. But many passengers would say that I don't mind paying a little bit extra, but I would like to travel at a comfortable time. So it depends on when you are traveling. Traveling at odd hours, traveling during weekend when you want to be with the family, that is having a higher time cost. And then there is the concept of defer time. Now, except when you have your own private car or when you can hail a taxi, in all scheduled transportation, whether it is train, whether it is bus, whether it is aircraft, you have to travel only when there is a bus or a train or a flight available. So let's say at 10 o'clock in the morning you get a call, you are in Mumbai, at 10 o'clock you get a call from some agency in Pune saying that please rush to Pune, we want you here. Now if I look at the calendar or timetable, I find that the flight is only at 4 o'clock, the next flight, which means I have to wait from 10 o'clock to 4 o'clock to be able to start my journey, and then I reach Pune maybe at 4:45 or 5, and then I have to travel another 1.5 hours. I am actually going to reach quite late. So even though it's a fast mode of travel, effectively it is very poor because I had to defer my flight from 10 o'clock in the morning to 4 o'clock. Why? Because there was no transportation available. Similarly, train. Now you might say last minute there is no train ticket available. So I have to defer it till maybe 2 days or 1 day when the train is, because I might go for Tatkal, that is also for tomorrow. So defer time is the time by which a passenger has to defer the journey to ensure that I am able to take that mode. With a personal car, there is no defer time. When you want to travel, you just go, pick up your car and start traveling. So, when you have your own personal transportation system, whether there is a driver that you have hired or whether you drive your own car, there is no defer time. And finally, as I said, there is a infrastructure cost. Now, in this particular study, we have ignored the effect of the discomfort cost because there was no way of bringing in. Also, when you access the airport or the railway station, you have to incur some taxi fare or some fare in transportation, which is called as the access cost. That also we have ignored. But we have looked at the time cost and the infrastructure cost, and I will explain to you how we have done that. So, now the generalized cost of air travel would be the flight cost or the cost of the ticket that you pay. Now, any airline will charge you a ticket price based on three things. First is whatever cost they incur per passenger per trip in operating the aircraft, whatever charges they have to pay at the airport per passenger per trip for using the airport, and they are a business, airlines want to stay in profit, so they will always charge or try to charge some profit. So, these three costs together will normally constitute the ticket. Now, I do not want to bring in the complication here of competition between 2 or 3 airlines, where you may even go below the operating costs because you would like to stay in the market or increase the market share. Those are extraneous factors. If we look at the true cost of travel, you will find it will be a combination of these 3 terms. Okay. Now, if we go deeper into operating costs, there are 2 components, the direct operating cost and the indirect operating cost. Now, if we look at the charges for the airport, in the airport what you pay a landing fee and you pay a passenger handling charges. Okay. So, at some airports there are different formulae, and we have a separate lecture on the components of the DOC and how they are estimated. But here I would like to just say that some part of the airport charges are already a part of DOC actually. Okay. But just to understand, airport charges normally that we pay are the landing fee and the passenger handling charges, right. Then as I said, there is an excess cost, that means the taxi fare that you pay to reach. Then there is a time cost. Time cost is basically what you do is you look at the total time spent in travel, the excess time at both the places, origin to the airport or airport or railway station or the bus station, plus time from the airport or the bus station or the railway station to the destination, that excess time, plus the flight or the train travel time or the bus travel time, and the time by which you have to defer your journey because of the non-availability of the mode of transport. All these 3 together is the combination of the time spent in travel, and when you multiply this by something called as value of time, you will get the time cost. And in case of an air travel, you have an infrastructure cost in terms of the airport, because some agency has invested money and created the airport in the first place. So, that particular cost of setting up and operating the airport, that has to be recovered. So, this study assumes that we are now setting up the air transportation especially from one established city to one new city, and we are trying to figure out what kind of aircraft to operate and what will be the required airport. So, in this study we assume that the destination does not have an airport. So, we have to incorporate the costs of setting up and operating an airport that is suitable for the kind of air transportation service we are planning to provide. So, this particular study looks at flight cost, access cost, time cost, airport cost, but the access cost is a fixed number in this particular study. Okay. Now, to incorporate all these things into a computer program for commuter and regional aircraft, a code called as CRAGER was created, and now I am going to describe to you this particular code. What is CRAGER? CRAGER is an acronym that stands for Commuter and Regional Aircraft Generalized Cost estimation routine. Okay. Now, this is basically a program that does two things together. It integrates the design synthesis, that is arriving at the aircraft configuration, aircraft parameters, along with the flight profile or the trajectory, and it optimizes both of them together. So, this is integrated synthesis or design synthesis and trajectory optimization routine. There are some features of CRAGER which I need to highlight. It is suitable for multi-stage missions. Now, what is meant by multi-stage missions? In a typical aircraft, you have a single stage mission where you take off from a origin airport A, climb to a cruising altitude, travel towards the destination B, and some kilometers before that you start descending and you land. So, the total distance travelled is 300 nautical miles, for example. This is a single stage mission, but you could also have what is called as a multi-stage mission. Here what you do is you travel the same total distance of 300 nautical miles, but you do it in two parts. So, you travel from A to a point, and at that point you may or may not do refueling. Normally when we have multi-stage missions, we do not want to do refueling at every point we touch, because that will be a lot of time wastage. So, you carry extra fuel in the first flight to take care of both the flights. So, you could do something like this, you can go from A to B, right, you can do it via a point, and then you can go from B to some point and then back to B. So, this is called as a multi-stage mission, wherein multiple flights are done by the aircraft over the period of time rather than one big long flight. Now, the CRAGER code has several modules, as I will explain to you in the next few slides. These modules, the beauty is that this is not just a theoretical calculation. The data that is used in these modules has been validated based on the data of 47 existing aircraft at that time, which were available for commuter and regional operations. Right? It has interesting modules called as the airport module and the airport cost module and the time cost module. The time cost module is very simple, you just multiply the value of time with the summation of time spent in excess, in travel and in deferring. The airport cost module is little bit interesting, and we will talk about it in more detail at the end of this lecture. Now, this particular program contains 20 design variables. Design variables are variables whose values can be changed by the designer or the user, because we want to investigate within some upper and lower limits what numerical value of this variable is helpful in giving us the best solution. Of these 20 design variables, 11 of them are related to the aircraft configuration, and I will show you the list very soon, but 9 of them are related to the flight profile or the trajectory that the aircraft follows. So, this is interesting, because in the normal aircraft design exercise, we do not normally look at trajectory related variables in the design process. Trajectory is fixed, mission profile is fixed, okay. We just look at the design configuration. Then CRAGER also has some constraints. Constraints are values assigned to some parameters which have to be either less than a number or more than a number. Some of them can be also equal to that number. So, the constraints where you have to have the value less than or more than some number, they are called as the inequality constraint. There are 4 such constraints in CRAGER which are related to the aircraft operation. And then there are 6 parameters which are basically derived parameters. They are the equality constraints in CRAGER. So, the CRAGER has to churn out the numbers in such a way that 6 parameters, their values are exactly a particular value which is pre-decided based on the specified equality constraints, and 4 parameters have to be less than or equal to a particular number. So, we are dealing with 20 design variables and 10 design constraints. And interestingly, we need to look at a penalty function approach to handle the constraints, because some of the methods which are used for optimization called as the indirect methods, they are not able to actually handle the constraints implicitly. So, they have to be taken care explicitly by specifying penalty functions. Have a look at the design variables in CRAGER. Okay. As I said, there are 11 which are configuration related. For example, wing area. Now, wing area, what do you mean by wing area? It is important to know that wing area basically is defined as the wing reference area, which is by convention the area marked in the figure, including the area inside the fuselage. So, projected area including that inside the fuselage, the top view of the aircraft. So, only one area, the top view of the aircraft, that area will be the wing area. Then we have wing aspect ratio. Wing aspect ratio is another parameter which is indicative of the slenderness of the aircraft wing. How slender is the wing of the aircraft? So, aspect ratio is defined as square of the wingspan upon the area. So, for a given area A, if the wingspan is larger, you have higher aspect ratio. If the wingspan is smaller, you have a smaller aspect ratio. Now, commuter and regional aircraft which are flown using piston prop, turboprop engines generally have an aspect ratio of around 13 to 14, around that order. Okay. Then there is something called as wing taper ratio. Taper ratio basically tells you how much is the change in the chord of the wing from root to the tip. So, it is defined as lambda, which is the ratio of the root chord tip chord upon the root chord. So, therefore, the value of the lambda will be 1 or less. It will be 1 if you have no reduction in the chord along the length, you have a straight wing, rectangular wing, the aspect ratio will be the taper ratio will be equal to 1. Okay. So, it will be 1 or less, and in some cases you define the taper ratio as the root chord upon tip chord, in which case it will be equal to 1 or more. So, depending on the value specified, you can make out whether we are using which convention. Generally, it will be tip chord upon root chord, and that is what we also will use in our study. Then the next parameter is the wing thickness ratio, that is how much thick is the wing at its maximum value compared to the total chord of the aircraft. So, if the maximum thickness is B located at a point C from the nose, the location does not matter. What matters is the numerical value of B as compared to the value of A. So, the thickness ratio is going to be B upon A. The next will be the wing leading edge location, and that is along in the top view of the aircraft, where is the wing located from the nose. So, the x value is the value of wing leading edge location, and it is expressed in terms of a ratio. So, you take the length of the aircraft as either L1 from the maximum point on the front to the back, or it could be called as L2. So, the value of the leading edge location would be x upon L1 or x upon L2. So, it will be a number which will be definitely between 0 to 1, generally it is about 30 to 40%. So, it will be 0.3 to 0.4 generally. Notice we have looked at only 5 parameters out of 11, and all of them are wing related. This is because in aircraft conceptual design, you have a lot of room to play with the wing and its configuration, and it also makes a huge difference. A typical wing is going to be around 12% of the total aircraft weight, and that is the one that gives you the lift that you need, and you would like to shape in such a way that the drag is minimized. So, therefore, a bulk of the parameters out of 11, 5 parameters are devoted to only the geometry and the features of the wing. Then we look at rear fuselage length. This is basically from the side view or in the top view, what is the distance of the rear fuselage. Now, notice that this in this particular aircraft, this is Dornier 228, the rear portion is actually conical, which is mostly true in many aircraft, because what you need the rear portion for is to move the vertical tail and the horizontal tail away, so that you get enough moment arm to give the moment which can balance the imbalanced moment. So, in some cases there is no rear fuselage, you have 2 booms through which at the end of the boom you mount the tail. So, the rear fuselage basically is keeping the tail reasonably far away from the center of gravity, so that the size of the tail and hence the aircraft weight can be reduced. The farther you are from the center of gravity, more effective will be the moment generation capacity. Then the next one is the takeoff flap deflection. This affects a lot of aerodynamic coefficient value, right? The coefficient values is affected. So, there are various types of flap and various deflection. Then you have maximum takeoff mass, total fuel mass, maximum takeoff power. Now, and balance field length. Now, please understand, maximum takeoff mass is something that you actually calculate in the design. Total fuel mass is something that you calculate in design. Max takeoff power is what you try to find out, and balance field length also is a constraint that you want to meet. But in this particular code, these parameters are given as design variables. There is a very interesting reason for that, which I will explain to you as we go ahead. Then there are also some parameters, 9 of them, which are trajectory related. The first one is climb throttle, between 0 to 100%. How much throttle do you give during climb? And then when you descend, what is the throttle in the beginning and how slowly are you allowed to come? Do you come like a stone, which is very dangerous? So, therefore, there is already generally some throttle given in the initial stages and also in the final stages. Then at what speed do you climb? At what cruise Mach number do you fly? At what speed do you descend? And at what cruise altitude do you cruise? So, these are the parameters, and then remember that we are looking at multi-stage aircraft. In a multi-stage aircraft, you will have one first stage and then there are multiple stages. So, it will be difficult for us to calculate the profile or for all the things. So, what we do is we calculate the parameters for one main stage and a notional stage which represents the average of the other multiple stages. So, how much of the fraction? Now, I told you that the best profile that is available for minimum fuel consumption is just sawtooth. You climb to a destination, to climb and then descend. But you cannot do that in actual reasons. There are two main reasons. One is the ATC would like to monitor you and they are happy if you maintain a constant altitude. So, because of ATC requirements, you might be forced to fly at some altitude lower than the optimum, just so that they know that you are in this particular location in straight horizontal flight. And the second thing is that the crew members are generally expected to serve the passengers some beverages, some snacks, water. So, for that they need time. They cannot serve you when they are when the aircraft is going in a climbing mode, because then it will be difficult for them to push the trolleys or to control the trolleys. So, serving of the passengers is normally done only when the aircraft is cruising. So, some amount of cruise is intentionally provided by the airline so that they can service the passengers. So, that number can be given here as a design variable which can be changed. Now, after having looked at the design variables, let us understand those 10 constraints in CRAGER. There are some which are operation related, such as the climb gradient. This is required to ensure that the aircraft has certain reserve power when it goes into a climb. This is a requirement which has come from the regulatory bodies. So, this is called as the weight, altitude, temperature, climb gradient. Then you have main cruise throttle less than 100%. Obviously, you cannot produce power more than 100%. Actually, during cruise you fly at a much lower throttle, but the limit is 100%, isn't it? So, therefore, we have given a percentage limit here, because in this particular code, depending on the throttle that you give, the engine gets adjusted with the power that is available for flight. Then many of these aircraft are unpressurized, and in these aircraft, if you come down very fast, the change in the ambient pressure from the cruising altitude to the ground happens very fast. So, the passengers will get earache or feel very uncomfortable. So, therefore, we have put a limit on what is the maximum rate at which you are going to descend. This constraint can be removed in case you are looking at a pressurized aircraft, but commuter aircraft are and regional also are generally unpressurized, generally. Okay. It's very difficult to provide pressurization in a commuter aircraft and also in a regional aircraft. Then you have noise values. Any aircraft should not create so much noise that it becomes an annoyance to the people. So, I have covered this in a separate lecture about the 3 types of noise which are measured. One of them is sideline noise, which is measured at 450 meters on the sides, both sides of the runway when you are operating. So, there is a limit of 94 equivalent perceived noise level in decibels. This is based on the noise regulations prevalent at that time. This affects the propeller RPM, it also affects the maximum thrust that the engine produces. Then these 4 are actual operation related parameters. Then there are some pseudo parameters or desired parameters, such as the static margin, which I would like to be 5% of MAC. Now, one can argue, somebody might say that no, this should be 10%, some might say it should be 8%, 15%, it is up to you. In one of the case studies, I put it at 5% of MAC, you can change this number. Now, here are some interesting parameters. Calculated max takeoff weight should be equal to the assumed max takeoff weight. Remember, there were 4 parameters in the list of design variables, which were actually parameters that you determine and not what you specify. So, this is an interesting feature of this particular code. In the normal aircraft design code, you do a lot of iterations. You change the parameters so that, and you iterate till the maximum takeoff weight is equal to, it converges to a value. Now, that takes time, and that can be very, it can lead to complications, especially if you have multiple loops. So, what we have done in this is, we have brought in a new interesting concept. We leave it to the optimizer to help us crack this problem. So, we say that the max takeoff weight is expected to be within some lower and upper limit. We tell the optimizer, you find the value of the max takeoff weight such that it meets the constraint and the assumed value is equal to the value that is calculated after all the analysis. Similarly, for the fuel, we are giving some range for the fuel, and we are asking the optimizer to find out what is the fuel mass such that the assumed value is equal to the actual value. And similarly, the distance that you travel, okay, we have given some range, but you will spend some distance in climb, some distance in descent. So, the remaining is available for cruise, okay, and we have also given a fraction of cruise. It may so happen that the 3 lengths that you do may add up to be more than the required origin destination distance. So, therefore, we give a constraint saying that the main stage length should be equal to the distance covered in climb, cruise and descent, because the main stage length is a parameter that you specify as a requirement. And similarly, for the notional stage, which is, as I mentioned, taking care of the multiple stage lengths. So, this is how we avoid the iterations in the design cycle. Here is the flow chart of this particular code, which has got these various modules. And now we are going to look at one such specific module which is of relevance and interest to the commuter and regional aircraft. Thank you for your attention.